Welcome everybody to GeoHug, and today is going to be such a good one. I am thrilled that we have Mikayla Sambrooks joining us today. So Mikayla is a geophysicist, having worked in greenfields and brownfields exploration for Newmont until just recently, and 2 weeks into her new role at Fleet Space Technologies. And it is going to be brilliant as she chats about why integrating geochemistry and geophysics is the first step toward the future for making more discoveries and mining deposits more efficiently. So this is going to be a fantastic session. I hope you all enjoy it. I will be promoting you up as panelists throughout the session. If you're able to come on through, please don't be shy. That way you'll be able to jump off mute and we'll have some discussions at the end. But yes, thank you so much, Mikayla, for joining. It's awesome having you here.
Thanks for having me. I have been so excited to come onto GeoHug for a long time. So yeah, glad we could make it happen, even though I was sort of in between, in between two different jobs. And yeah, this is going to be so much fun. I'm so excited.
No, I can't wait to hear from you today. So thank you for taking the time. I'm glad we made this happen.
Yeah, me too.
I was curious though, what got you into geology and geophysics to begin with?
Yeah, very common sort of story that a lot of geologists tell. Wasn't planning on going into geology or didn't even know what geophysics was when I started uni. Loved science, knew I wanted to go into science, but yeah, first person in my family to get to university or go to university. And yeah, when I got there, the biology, chemistry, math kind of basic subjects just weren't what I expected at the uni level. And I wasn't doing as well in those that I was when I was in high school. And yeah, I did some earth science subjects and absolutely loved them. Had so much fun, got really good grades, and I was just like, well, this makes sense. I need to stick with this if I'm going to make any kind of successful career out of anything. So from that moment forward, I took every single earth science related subject that I could, and it clicked. It made sense for me. Just being naturally curious about how the world works, and yeah, it just made sense. And the rest is history.
Love it. I love it. And you have so now you're working in tech and you've been in brownfields, in greenfields. I'm curious what some highlights are for you so far.
I've been exceptionally lucky in my very short career. I've had some really amazing experiences. I started working in North Queensland as soon as I finished my master's and was doing field work. So I got thrown into the deep end of doing field work in the remote kind of locations and doing long stints and that kind of thing. So yeah, that was amazing. And then I started with Newmont or Newcrest at the time. And I spent almost 2 years up at Havieron, which is sort of prelude to one of the topics we'll talk about today. But yeah, spent some time doing FIFO to Havieron, which is inland from Telfer, if people don't know. And that was amazing. Doing everything from, navigational diamond drill programs, the assay, I was looking after all the QA/QC stuff. So that's where the geochemistry sort of experience comes in. And, apart from the amazing scenery and sunsets and sunrises that you get to see, just the really smart people that I've been able to work with are absolute career highlights for me. I've been very lucky. Let me just say that I've had some amazing mentors, supervisors over the years. So yeah, and I just love learning. So I've been provided with great opportunity to just learn lots since day one. And I've just been a sponge.
Oh, I love that. That is brilliant. It's such a fun time when you're just like absorbing it all, experiencing it all. It's that's awesome. I'm glad you're having some fun. And I'm
Always.
curious if you've collected any good pet rocks along your travels so far.
I have so many. I don't know if you can see. There's a few on my table behind me.
Just a couple.
I've picked two that one is my favorite pet rock, and the other one is just one that I think will be kind of relevant to today's talk. So this is the first one, and it's a pyrope garnet. And the reason it's my favorite, this is from Broken Hill. The reason it's my favorite is you can actually see the crystal faces.
Yeah.
So you can see how that's not cut, that's naturally formed crystal faces on the garnet. So the amazing thing to me is to think about the fact that you can see that crystal structure. This is like one giant crystal, one giant mineral. So it just shows that on that macro scale, how, you know, minerals can be microscopic and we need a little hand lens to look at them, but sometimes they can just be massive like this. And it's just, if they're allowed the time and pressure and everything to grow and form these crystal faces, they do. And I just think it's amazing. And it's a really heavy paper, like it's a good paperweight. This other one, yeah, not one of my favorites, but I think it's just kind of interesting. This is actually just natural silicon.
Oh.
So it looks like a metal. It has a metallic kind of like luster, sheen, but it's really light. Like this is so light, and it's not a metal, it's silicon. So it's just has this really unexpected look to it. And when you hold it in its natural form, it's just, yeah, super not what you would expect. But we'll talk about silicon today a little bit. And yeah, I just think it's just cool. So yeah, there you go.
That is awesome. I think everyone liked that one. There was emoji central up the screen. Cool.
I will just clarify that I bought that. Okay, didn't find that naturally occurring, because you will never. Well, yeah. Anyway.
That is awesome. Well, thank you so much. Yeah, again for coming on today. I cannot wait to hear from you, and I'm grateful that you're taking the time. So thank you. And yeah, if you want to share your screen, and we'll get stuck in.
Hi everyone, I'm Mikayla. Yeah, today we're going to look at some big picture stuff. We're going to take a few steps back and just think about things from a systems approach, I think, and just to maybe give you hopefully a different perspective on collaboration and integration that you hadn't had before. At least at the very minimum, I just hope to spark some ideas and conversations. So yeah, really excited. Oh, that doesn't work. Okay, we're pressing. There we go. So I'm starting with, you know, what everyone else is really starting with these days, and why do we even need to talk about integrating geochemistry and geophysics? Well, it's, you know, it's pretty clear that the demand for minerals is increasing and deposits are getting deeper and harder to find. So I think a lot of people have probably seen this poster that BHP put out, and it just highlights that reality. And that was before the extra pressure put on our industry to find more minerals to support the AI advancements that have really taken over in the last 5 years. So now we have this extra pressure, as I said, from AI advancement, and we need to find even more probably to sustain that demand. So there's this there's a funny irony to this, where actually the very thing that's putting pressure on our industry can be the thing that helps us find those deposits. But in order for that to happen, I think the first step is to collaborate, and we need better, cleaner, integrated data to be able to leverage those new advancements in technology. That's why we need to go beyond the silos. And I just want to acknowledge that, you know, there are a lot of other niche disciplines like metallurgy and petrology and data science, hydrology and, you know, geotech, all of these things that, you know, they've evolved within their silos to tackle really kind of niche problems in their areas. So, and that's fantastic. But I think the problem with that is that we often stay in our lanes, and, you know, we go to conferences that are to do with our own disciplines, and we don't often see the advancements that are happening in our sort of brother and sister disciplines that are just across the pond. And yeah, so I think we need to go beyond the silos and just be better at collaborating. But acknowledging there are all these other great disciplines out there, but I'm just talking about geochemistry and geophysics today. So we're going big picture, but we're starting at the smallest possible end of the scale that you can. All right, so we're going elementary particles here. And if you don't know much about elementary particles, if we split it, we have fermions, which are related to the matter. So those are things like your electrons and protons and neutrons that make up all the different atoms, including gold and copper and iron, all the different types of elements. So different combinations of electrons and protons and neutrons will create different atoms. So it's that structure, that different atomic structure, that forms different types of elements with different properties. And then you have the bosons, which are the force carriers. So I like to think about it like we're really looking at how matter is interacting with energy. And there's this theme that I'll carry throughout the whole presentation, where we're talking about structure and behavior. And this is kind of where I think fundamentally about geophysics and geochemistry, and something, the structure is governing how that matter behaves or interacts with energy. So that's why we're starting at elementary particles, and hopefully you can keep that kind of structure and behavior theme in your head as we go through. So, as I said, different combinations of subatomic particles come together to form different atoms. So, for example, silicon, which I just showed you before, aluminium, oxygen, and iron. These four elements alone make up more than 80% of our crust, so of the Earth's crust. So where we actually go looking for mineral deposits is in the crust. And really, when we're mapping the crust using geophysics or geochemistry, whatever kind of analytical methods or mapping methods that we're using, we're on a large scale, by and large, we're mapping the distribution of these things. And specifically, if we look at silicon and iron, because of their atomic structures, so they're different numbers of electrons in their outer valence shells, and these things dictate how these elements manifest in their behaviors and their physical properties. So iron is much more dense than silicon. It's magnetic, it's conductive, and that's due to that atomic structure. So I also just mentioned that this table is coloured by the Goldschmidt Goldschmidt classification, and it's coloured the elements by what other elements they like to hang out with in the crust, and how they sort of are likely to bond together. And the lithophiles are they're the crust loving elements. They're much lighter. They like bonding with silica and oxygen. And when we have planetary differentiation, everything like sinks or gets buoyant. So that's when everything's separating. And it's the siderophiles and the chalcophiles that we're really interested in the exploration and mining game. They're the ones that are after, gold, copper, silver, all of these elements that we need more of in a big way. So we're thinking about a really big thing here and looking at mapping the distribution of things like iron and silica in the crust, but it's also just bringing it back and realizing that there are all these other elements and different atoms come together to form different minerals. And now you can start to see how complex, okay, this is like so many different combinations of these atoms and elements can form different minerals. And then each of those is going to have a very different physical property or a behavior, and the way that that mineral interacts with its environment and the energies around it. So it's not as simple as just mapping silica and iron. It's actually quite complex, and that's why the mining and exploration game is not an easy one, and there's a lot to think about. So carrying on with the theme of iron, we're looking at 4 different iron-bearing minerals that are pretty common in alteration and mineralization, and pretty commonly associated with different mineralized deposits. And those are hematite, magnetite, pyrite, and pyrrhotite. And we're only looking at 3 different atoms here, 3 different types of elements, so iron, oxygen, and sulfur. But we have 4 very different minerals. Look at their properties. So we have conductivity, chargeability, magnetic susceptibility, and density. And I'm just showing sort of a relative like low and high, how these minerals manifest in those physical properties. But essentially that is governed by that crystal structure. So how now that the atoms are coming together to form a mineral, that structure is dictating by and large the physical property of the mineral. So we've got the same atoms, but how they come together and how they form a structure, that's dictating the physical response of that mineral. And now we can already see how geochemistry and geophysics are only telling you part of the story, really. So the geochemistry is telling us what abundance of different elements that we have. So generally in an exploration program, like early on, there'll probably be some geochemical analysis, and depending on what type of lab analysis methods that you pay for, if it's a mass spectrometry or X-ray diffraction, you might get some abundances of ions and minerals as well, but mostly you're going to get different atomic abundances. And you're not going to necessarily know whether you have magnetite versus hematite or pyrite versus pyrrhotite. This is where your petrophysics can come in and help you differentiate based on those physical properties what mineralogy you might have. So I guess the point here is that a lot of the time geochemistry doesn't directly tell us what minerals we have, and the same can be said for geophysics. We don't really know directly what minerals we have present based on a geophysical survey or a petrophysical survey, but we can make inferences and we can be very smart about, with geochemistry, mass balances and fancy kind of equations to calculate what minerals we think we have based on the elements that we have. And conversely, with geophysics and petrophysics, we can do inversions, and we can have a best guess of what minerals we think are present based on the properties and sort of the broader geological context. But really, they're both telling us different information about the same material that's there, and one without the other is not the full story. We need both. So, I also wanted to talk about the fact that we get other information from this, like magnetite versus hematite, for example. Hematite is the more oxidized version, or a lot of people akin to rust kind of thing. So it can tell us about the system as a whole. So like, is the system more oxidized or reduced, for example? It might be able to tell us something like that. The other interesting thing, I think, that structure plays a big role in here is, so pyrrhotite is an interesting one in its own, because its structure, and it can have a few different versions of its own, of the one mineral having different versions of its structure. But it has that one X in the brackets there. I can point this means that the structure just allows lots of other different types of atoms to come into the structure. And it means that pyrrhotite is susceptible to become remnantly magnetized. So if pyrrhotite is forming when our magnetic field was reversed, then it has the potential to form like a permanent magnet, basically, and lock in that remnant magnetization. So yeah, it's just a really unique kind of interesting property that is dictated by structure. That's just unique to pyrrhotite, and something to keep in mind for the rest of the talk. So now I want to just walk us through a generic exploration program from an early stage through to like a resource definition. And we'll just talk through some of the ways that we've always done things in exploration, and typically some of maybe the inefficiencies or things that we could improve upon. So typically, if we have a greenfields target, at this stage, we'll have regional geophysics and geochemistry surveys. We may already have this from the government. If you're in Australia, lots of great pre-competitive data. Maybe you've already assessed that data, and now we're at the tenement scale, but we need to collect some still regional but tenement scale data, so that we can really know where we want to look and hone in on from that broader area. So we have large coverage geophysical surveys, typically lower resolution. So the type of geological features we can resolve with these regional surveys are big regional structures, things that are really like massive faults or basins or intrusive complexes, or just really big things. We can't resolve anything nitty gritty, because the resolution of these surveys is just this data is fit for purpose. It's designed to show us on a broad scale what's happening and allow us to know where we want to look deeper and get more detail. And we might have, I've spoken on the geophysics, but for the geochemistry, we might have like a soil survey or a stream sediment sample, that kind of data set for the regional point. And that data is still really, depending on the lab methods used, precise and accurate, but it really is only local to that point, and we can't really infer anything about the geochemistry away from that point. So we don't know if 2 points, if it's continuous between those 2 points, or if it's patchy. So in this example, let's say we have 3 of our geochem points are like 3 magnitudes above the rest of them, and they're like 3 that are next to each other, even though they may be 100 meters apart. We think that there's a higher chance that this is a real anomaly, and it's coincident with, say, we have a regional magnetic survey, so we have a coincident magnetic anomaly, and we have a geochem anomaly. So we think this warrants some follow-up. We definitely think that this is a real geological feature that's causing this anomaly in our geochem and our geophys, and we think it's worth following up with a drill hole. to know for sure. So we follow up, we stick a big diamond drill hole into this, and we recover core, which is invaluable. We get to identify structures, alteration facies. We can identify things on the micro scale and on a deposit scale. And, you know, in this case, we have 30 meters continuous of like 3 grams per ton gold. So we know we have something mineralized here, and we just don't know if that extends past the hole that we drilled. So really amazing, because we have this like point of truth and this data that's accurate and precise, and it's telling us everything we want to know, but it's telling us only in that drill hole, and we can't infer anything really away from that drill hole. So at this point, we know we've got mineralization. We just don't know how continuous that is or how extensive that is. And we've got all this regional data, but we still can't really interpret anything detailed using that, even though we have this drill hole now, because the resolutions are just not, are not akin to each other. So now we've got to collect more data. So now it's time for that definition infill data collection period. We know there's something worth, following up here, but we just want to know, we wanted to better define it. We think we might have a porphyry, for example. So, we want to know where to put the next drill hole without wasting money and without, we want to make sure that the next drill hole that we drill is going to provide us with new information, not just exactly the same information that we already have with the other drill hole, but new information. So luckily, we can also, take some petrophysics. We took some petrophysics measurements on our core that we drilled. So we have an idea about the sort of physical properties of our mineralization now, and we've now collected some 3D IP geophysics on a tighter resolution, and we've recovered a 3D chargeability model for our porphyry deposit. And we have a more detailed high-resolution geochemistry survey too, which reconfirms, yep, we've got a sizable deposit here, definitely going to, turn into a resource. So now it's going to be a pin cushion, and there's going to be a million drill holes into this thing to define it, and eventually it'll become a mine, which is all great. This is sort of what we've always done. This is the natural progression of things. But then we get stuck because, okay, we have this deposit that's being developed into a mine, but we need the next deposit. We need the next deposit in the pipeline. Where's the next one going to be? We need to be able to pay for this drill out with new stuff coming in. So where do we look next in the tenement? That's what I would ask the audience, and I'd be interested to know what they say at the end. But keep that in your head, like where do we go next? Because the regional data, we probably made some maps based on the aerial mag, and that map will probably be taken forward as the point of truth, and really we've picked the best anomaly based on the regional data already, because that's the one that we've developed into a mine. So if there are other porphyries on our tenement, how do we know where to look? If they're concealed, or what do we do next? So now I want to talk about a real example in exploration. So this is the Havieron deposit, which I mentioned earlier that I worked at a couple of years. And I think it's really analogous to a lot of the types of deposits that we will have to go looking for, especially in Australia. This is 450 meters undercover. So these are the types of deposits that we're probably going to be going exploring for. And Havieron is a reduced intrusion-related copper gold deposit. It is about 60 k's inland from Telfer, which is a famous 25 plus year operating gold mine. Havieron was drilled in the early 90s. I think it was 1991 by Newcrest, and they just didn't drill deep enough. They didn't know how deep the cover was. They knew it was deep, but didn't know, how many hundreds of meters do you want to drill into sand before you give up? So they didn't know, it wasn't deep enough. Almost 20 years later, Greatland Gold came back and extended the drilling and hit the mineralization. So just backtracking a little bit, Havieron presents as this coincident magnetic and gravity anomaly in the geophysics. Obviously, there's no geochemistry at the time because it was so deep undercover, and there's just no like there was no way of getting that data. So drilled based on a geophysics anomaly, finally drilled further to actually hit the mineralization that they thought was causing that anomaly. And so then Greatland was like, okay, let's forward model the geophysics. So they did a simultaneous forward model of the gravity and the magnetics, which is this top model up here. And you can see the blue is the magnetics, and it fits really well, almost perfectly. And then the red line is the gravity. You can kind of see to the south and to the north, there's just like a little bit of an offset. It's just not fitting perfectly. And the body, this green one is the geological feature that they're modeling to try and figure out how big is this this deposit, or this geological feature that's hosting our mineralization. How big is it? Does it dip? Where is it? All that kind of stuff, so that they could inform their future drilling and, you know, not waste money on drilling holes. So there was 2 clues that gave them an inkling as to why this top model wasn't the true scenario, was reflecting what was happening in the subsurface. One of those is that gravity couldn't fit. So really you want to be able to fit to both of the data sets as well as you can, but it's not fitting. And the other thing is the magnetic response. This is a total magnetic intensity. Generally, when you have a magnetic anomaly in the southern hemisphere, you'll get a dipole effect. So you'll get like a mag low on the south side of your mag anomaly. And that's not the case here. So that's when they thought, okay, maybe there's remnants here. And because they had now drilled into the mineralization, they confirmed that actually Havieron has a lot of pyrrhotite. It's pyrrhotite dominant, and it's iron-bearing mineral. So if you remember what we spoke about before, pyrrhotite is susceptible to remnants. And so now they've modeled again with that mineralogical knowledge included and the remnants. So the new model fits the gravity and the mag like perfectly, so you can see. And now the geological feature of the body that they've modeled is more like vertical. And so you can see how thinking about the mineralogy as a geophysicist can save lots of money, because if they had have drilled into this, they just would have kept drilling into metasediments and maybe a dike, but yeah, wouldn't have hit mineralization. So it's a really important takeaway here, I think, is that as a geophysicist to think about the geochem and the possible mineralogy, and conversely as a geochemist to think about what kind of geophysical or behavioral responses you might see manifest. What could they have done in the 90s, like in the early 90s, to know how far to keep drilling? Probably not much. But one of the things I'm really excited about with Fleet is this joint gravity ANT method, which basically uses your ambient noise tomography data to know where that cover is, where that cover layer is, and then be able to include that with some kind of knowledge of your petrophysics to know what your density is, run your gravity inversion with that knowledge so that you're just inverting for the densities to resolve the rocks that you are interested in, which is below the cover. So if they had this back then, they would have known how deep to keep going to make sure that they were hitting mineralization. But, you know, it's one of those examples where, you know, Havieron is analogous to the types of deposits we're going to be searching for in the future. So this technology is available to us now, and I would hope anyone would use that kind of method to know how deep they need to drill, or to even, you know, save on drilling and just air core down to the bit that you need if you can. Okay, so I've spoken about how we use energies, or we use how matter interacts with energy to analyze the universe around us. So this is the scale of everything. It's a little bit overwhelming. It includes the biggest things that we can detect that we know exist in our universe, like different galaxies, to the very, very smallest things that we can detect that we know exist, like subatomic particles. And a lot of the time we only know, like subatomic particles, we only know they exist because of how they interact with energy. We can't actually physically touch a subatomic particle or detect it. It's how it's reacting or interacting with energy, and that's how we know that it exists. And it's kind of the same for all types of analytical methods and whatever material that we're looking at. And the interesting thing, so muons, great that I hope people got to go to Mark's talk earlier, but so muons are those really, really, really high energy particles, I guess. So they're higher energy than gamma rays and X-rays. So they're up here, but they're really unique because they can because of the speed that they travel, they can penetrate much deeper than gamma rays and X-rays can. So typically gamma rays and X-rays, they can't go very far into material, but muons are very special because they can do that. So definitely something that I'd keep an eye on for future just technology kind of things. But yeah, it's an interesting side note. But yeah, so we use, this whole energy spectrum to analyze the universe around us, and at all different scales of things. So, from the tiny, tiny things that we can't even conceptualize to the biggest that we can't conceptualize. And the interesting note here is that the visible light spectrum, so the stuff that we can actually see, is just this tiny little sliver here, and it's in between the UV and the infrared. And that is still, just as important for analysis in general. This is the bit where we get to go out into the field, pick up rocks, identify minerals like we did at the start with our eyes and what we can see. This is the visible light spectrum. So there's also a lot of methods that use energies in the visible light spectrum, including multi and hyperspectral spectra in general. So the part that we're really exploring for, the point in the scale where we're exploring for deposits, is actually only just in here. So it's somewhere between rocks and planets, right? We're looking for, people say camp scale or deposit scale. That could really be anywhere between a 5 meter vein that just hosts like gold to a 5 kilometer porphyry kind of intrusive deposits. So yeah, somewhere in between there, that's where we're looking and we're searching. So why don't we just use methods that use energies and frequencies, like the short and long radio? Well, obviously it's more complicated than that, and we use methods that use the whole spectrum, but also the resolution part is really important, because it would be not really useful to know, well, it would be really useful if we could know exactly all the elements distribution in the subsurface at every point to depth. That would be great, because then you wouldn't need geologists. Maybe I shouldn't have said that, but yeah, it's not that simple, right? It's more complicated than that. Oops, oh no, went to the last slide. Okay, so this is a very, very gross exaggeration and simplification of the methods that we use in exploration and mining. The top layer is your geophysics, you've got your spectral data in the middle there, and then you've got geochemistry on the bottom. And I'm just showing like resolution now. So some of the different methods that we use at different resolutions and fit for purpose for different type of challenges or problems that we're trying to solve and answers that we're trying to get to. So starting off with geophysics, we can basically customize a geophysics survey to the biggest, the highest resolution or the lowest resolution that you want, depending on your source and receiver. And obviously we use natural fields like electromagnetic fields and gravitational fields, but we also use active methods that we're creating our own type of energy to either inject into the ground or for the matter in the subsurface to interact with in some way for us to be able to detect it. I've been really cheeky here and put in spectra in the middle, because I think spectral data is really an interesting link between geophysics and geochemistry that spans across a lot of the same resolutions and scales that geophysics can, but tells us something about the mineralogy directly. So, as I said before, our geophysics is inferring our mineralogy through, what we know about the physical properties of different minerals, and geochemistry through, very fancy mass balance equations and that kind of thing can infer our mineralogy from how much of each type of element we have. Spectra is so cool because those crystal structures and the way that they vibrate and the way that they interact with energy, we're able to detect what type of mineral groups there are almost directly, and at lots of different scales. So at the lab scale, down at a microscopic kind of level, we can identify minerals. We can also identify groups of minerals at a regional scale. This scale is a little 2-kilometer line here. So this is cuprite in Nevada. So this is like a big hill, if you imagine this being the ridge. So yeah, it's just this interesting link that spans across all these scales. Now the big caveat of spectra is it's only penetrating, or it's only really looking at the very surface of things. So we can't really infer anything deeper than that. So apart from where we have really deep cover, like places like Havieron, anywhere that we don't, we could potentially start with our hyper or multispectral data to know what kind of minerals we have present. And if we combine geochemistry and geophysics with that, like, we've almost got the whole picture, but it's just at the wrong resolution that we need. So at the other scale, or the other end of that, if we do have a drill hole, even if it's just one drill hole, if that drill hole goes through all the different types of lithologies in our area of interest, including the stuff that's not mineralized, and we have a downhole petrophysics, either a wireline log or even handheld. Wireline would be better to compare with if we had some kind of scanning tool, like spectral scanning tool. I'm not going to name names, but there are lots of them out there now. And if then you combine that with our assay geochemistry, we're able to then use that data to train at the smallest scale, train our deep learning neural networks with that real data. And it is getting so smart now to the point where it can pick up these relationships that maybe we as humans probably can't pick up on. And so we can train ML on these real cases. And eventually, if we have enough good, clean, representative data, we can hopefully use the geophysics, which gives us sort of a volume or idea of the volume in the subsurface in terms of different petrophysical properties. For example, 3D active seismic cube will tell us about different impedances and velocities and densities essentially in the subsurface and to a depth. So if we have that trained data using that one drill hole, then we could infer what mineralogy we have away from the drilling. So that's really powerful, because this now allows us to, at that example at the start where I was walking through, we've got regional data and then we have the drill hole and then we take some infill data. Well, it kind of allows us at that initial stage to skip a few steps and maybe predict some mineralogy away from the drill hole, provided we have some good representative data to be able to train on. So really, really exciting stuff. And yeah, I do think that spectra could be the missing link here. So the way forward really brings all of that together. And I think the first step is plan together. I've seen a lot that geophysical surveys are designed, planned, executed by geophysicists by themselves, in solidarity. And the same goes for geochemistry. So the geochemistry surveys are planned, executed, interpreted, I think all by the geochemists. So rarely do a geochemist and a geophysicist get together to plan their surveys together. But I think that could be really powerful, because you're starting to think about the future-proofing your data, and thinking about who might use this data again down the track, or how might we reintegrate this data back into, when we get new data in our infill part of the exploration program, how can we then use this data? Or you're making sure that the investment that you're putting into this data is actually going to keep giving back. It's not just going to be used in this one way and then kind of forgotten about and sitting on a server somewhere forever. So planning together, thinking about the longevity and the future of that data. I think also using a statistical analysis to help us understand our data better and make sure that the investment we're going to get a return on that investment. So, how many data points do I actually need for the results to be meaningful? How does the data actually represent all the different rocks in my area? Am I being biased by only collecting data on the mineralized stuff? what are the range of the values that I expect to resolve in my geochemistry or geophysics? Like, what do I expect, and what do I think an anomaly would actually be? How many magnitudes of difference does it need to be a real something that needs to be chased up? These are all questions that should be asked before the survey is taken, so that when you get that, you can perform this analysis and know really how effective is this data set. And yeah, keep leveraging new technology. There is a lot of new things happening and being released every single day. And there's opportunities to use old data in new ways. There's opportunities to improve efficiencies by standardizing processes and automating workflows that can be automated. Things that don't need the human brain to sit there and go, oh, does it need to be this or this? Like, there are things that we just do every day that could be made more efficient. And when we're using this new technology, I think we need to train with real data, and we always need to validate against knowns. So we need examples that we know about to be able to validate, are these models doing this data justice, and are our predictions going to be meaningful? And finally, interpret the data in collaboration, not isolation. So when you get the data at the end, the geochemistry or geophysics data, sit down with a geochemist or with someone that knows a little bit about. If you're not sure, they might have a piece of the puzzle or a piece of information that could change your whole perspective on that data set. So yeah, it's all about collaboration. And these data sets are really complex, and they span a massive scale, like we've just seen. They have different dimensionalities. So combining them is a challenge, but it is possible if we think about all these things really carefully, and if we actually collaborate with our other subject matter experts. So there's some really exciting things happening at Fleet, and one of those, if you go to the website, is the Agile Geoscience page. It tells you a little bit about some of the stuff we talked about. But yeah, this is the direction and the way forward that I think the industry, reluctantly or not, needs to go. So yeah, that's me. I'm ending it there. I have a slide full of references if people want it, but it's just ugly, so I'm not showing it.
Brilliant. Thank you, Mikayla. I really appreciate you doing that. That was awesome.